Future distributed radio infrastructures hold promising potential for positioning and mapping, which can be leveraged for efficient beamforming and robust communication even under user mobility. We acquire synthetic aperture channel measurements in a realistic hallway scenario, where we subsequently measure the channels from a single antenna agent to 15 anchors, each equipped with an 8x8 antenna array. We perform angular delay direct positioning and mapping to jointly estimate the position of the mobile agent along with two walls in the environment that cause dominant non-line-of-sight reflections. Strong multipath propagation and obstructed line-of-sight conditions are characteristic for indoor radio channels. We record a trajectory where the mobile agent moves around a shelf filled with highly absorbing material. While it is initially in strong line-of-sight conditions, as the agent traverses, it gradually moves into obstructed line-of-sight conditions. Robust positioning of the agent, even in obstructed line-of-sight conditions, can be achieved through non-line-of-sight components, which are rays that are reflected off walls. We implement Bayesian filtering approximately using a particle filter, where we jointly estimate the three-dimensional agent position and the three-dimensional position and orientation of two walls that have a dominant influence on the multipath channel. Our estimator quickly converges to the true agent position and estimates one wall through the first-order reflection of the agent signal at its surface. After some time, it also correctly estimates the second wall, which is visible only by a second-order reflection of the agent signal that bounces off one wall and then the other wall. After channel estimation, we perform channel prediction, which means that we predict the future agent position and then predict channel state information parameterized by the predicted agent position and environment geometry. For all time steps along the trajectory, we compare the efficiency of a geometry-based beamformer with a reciprocity-based beamformer. The efficiency of phase-coherent beamforming depends on the quality of channel state information available. Having no channel state information, the statistically expected performance is the CISO efficiency, which is the baseline efficiency at which a random beamformer or an equivalent single antenna infrastructure would operate at. Having perfect channel state information would result in the optimum MISO efficiency, which leverages the full array gain that is identically equal to the number of array antennas. This is the efficiency range that we typically operate in. Having noisy measured channel state information, the performance degrades on expectation by a factor SNR over 1 plus SNR with respect to perfect channel state information. This corresponds to the efficiency of a reciprocity beamformer, which depends on random noise realizations and is hence augmented by a 98% confidence interval. At a constant noise power and decreasing signal power in obstructed line of sight, we observe that the SNR and hence the efficiency of a reciprocity beamformer decreases even further. After convergence of our state space filter, our geometry-based beamformer using predicted channel state information immediately outperforms the reciprocity-based beamformer in this low SNR scenario. It is able to do so because it incorporates physics-based channel knowledge. Under user mobility, the measured channel state information ages from the current time step to the next. The reciprocity-based beamformer given outdated channel state information incurs another significant loss if the channel state information is only a single time step old. Our channel prediction, on the other hand, uses a motion model to first predict the next agent position and second predict channel state information for the next time step. We can easily predict channel state information 1, 2, or 3 time steps to the future at the cost of only a marginal loss of efficiency. This demonstrates that our channel prediction can perform robust beamforming even under device mobility.